having a good time, enjoying a nice workshop. So I think you'll thank the organizers for the invitation. And so, yes, this is talk is also about flocking or swarming. And so my job here is to try to tell you about our current understanding about the dynamics of natural swarms. So this is mainly about our theoretical understanding, but to explain that, I will have to summarize a little bit the experiments that were done first. And so this will be like a summary of our work that has been taking place for about 10 years. So clearly many details will be left out, but I wish to just state the main, our understanding right now. So let's start with some experimental results. These results are, I left the collaborators' name for the last slide, sorry, but the results are by the Andrea Cavagna group in Rome. I will have the names at the end, I'm sorry. So basically, what have these experiments told us about? So these are midges, definitely not a pretty guy. They form swarms, that is, they fly together, but without order, without going to any particular place. They just fly around. They stay about for some time. These experiments are in the field, so they are natural swarms because they form in the parks in Rome during the summer and spring. So this is just they put a screen behind. This is a black screen behind, so to get a better contrast for the videos. And then with a system of 3 pairs of cameras, the experiments can convert these images to 3-dimensional trajectories, so resulting in space and time. And that's not easy to do, but it's done. And so basically, my contact with the data starts here, where we already have these nice trajectories, and one can start analyzing what these guys are doing. So the first thing you can do is you can ask, you can compute the average, the velocity, and you can ask, basically, are they going anywhere? And they're not going anywhere. So they're not a flock, they're not flying, they're just staying there. But it's also important to know that they're not just gas of insects. I mean, they are doing things. They have non-trivial correlations. If you compute the correlations, so this is the connected correlation. So you subtract the average velocity, which is very small, but anyway, you subtract it. And you compute the correlation of the fluctuations, and you find things like this. These are for different species that you find in the wild. But all these show that the correlation is much longer from what would you expect from the red line, which is just a random walkers or random flyers. So the order of magnitude is that we're using this intersection here as a measure of the correlation length. It's not the best measure, but anyway, it works. But so this is about a third of the size of the swarm. This will mean, as I will show, that these correlations are scale-free. But so it's not. It's pointless to argue whether R naught is large or not with respect to the size of the swarm, because we can give different definitions that will change the scale. The important point here is that you can measure the correlation length for swarms of different sizes, and that this correlation length scales linearly with the size of the system. So in that sense, the system is scale-free. There's no intrinsic correlation length. The size of the system is the correlation scale. So in that sense, the system is scale-free. When the system, if one looks at an infinite swarm, one would have an infinite correlation length. So, and this is what happens. We know that these kind of things happen when we observe a physical system at criticality, at the second phase transition. So that's one result. The next result is then you can go on and study time correlation. So you can compare the fluctuations in velocity here at some time and at some time later at another point. Yes, and you can define the time-dependent dynamic correlations. And if you do that, so you can measure relaxation time as well as the correlation length. And what you find is that the correlation time grows with the correlation length. So you find, in other words, you find critical slowing down, exactly as in critical phenomena in condensed matter in statistical physics. And you have exactly this law here where correlation time is proportional to some power of the correlation length, which is called the dynamic critical exponent. Actually, you can show more. You can show that this scaling it's obeyed beyond this law. The actual scaling form of the time correlation, but it's obeyed. But for this purpose of this talk, I will focus on these because the main player here will be this exponent, this dynamic critical exponent, which from the experiments comes about 1.3537, which is different from the known models, the known dynamical models, which I will come later. So in principle, this hints that there might be a new universality class at play here. So that's the second piece of experimental information. The third piece is succinctly put here, and basically is that if you plot the correlation function at some fixed time correction function for some fixed wave number, you get a behavior that's like this, that's oscillatory. So it's damped, of course, but you have oscillations, you have crossings of the zero, which is quite unlike what you find when you try to do the same with the Vic-Seg model. So you can, if you can pick the Vic-Seg model, which fortunately Ronald has explained for us what it is. So you can pick the Vic-Seg model, you can go critical, you can tune it to the critical point where the system starts ordering, and you can compute this, and you can explain the statics, you can explain the correlation, the scaling of the correlation length, but you don't get the right dynamics, because you don't get these oscillations, and you also don't get the right critical exponent. So, in a nutshell, these are experiments. This took quite a while to do and to interpret, and so this, but these are the ideas, and this picture is what now we are trying to put together into a coherent theory. And what I will try to tell you that this theory needs three things. So here, so the theory must account for the presence of scale-free correlations, so static scaling, critical slowing down or dynamic scaling, and underdamped effects or inertial effects. Okay. And our understanding is that to get this, this is kind of summary of this is the critical exponent. Yes, this new critical exponent. To get this critical exponent right, you need to build a model that has alignment, ferromagnetism, let's say, activity, and inertia. And so, when I said you need these three things, I mean this in the sense of Miniman models, in the sense of the renormalization group. I mean, if you leave one of those out, you go to different universality class. You get the exponents wrong. Right? So I will be showing you a minimal model, actually an effective mesoscopic model. But the point is, if you want to build this model, you have to put these three things. So I'll start one by one, putting these things and show you what you get. And well, points 1 and 2 are actually not our work. They are known. Of course, ferromagnetism is known for a long while. But then we are going to add inertia. But so that we can understand, let's start from the beginning. So the basic ingredient is alignment. Alignment is reasonable to put in because I've said Vic-Seg model gives you at least the right statics. So even if this system is not ordered, but if you can explain it by looking at a phase transition point of a Vic-Seg-like model. So we start with alignment. If you only have alignment, so you have a model like this, this is a classical Heisenberg model, and the dynamics was studied long ago, beginning in the 70s or probably earlier. So you can just write a Langevin equation for classical vector spins with ferromagnetic interaction. That's the minimal model for a magnet. To study the dynamics, to do renormalization group on these models, one actually does some cost graining and proposes a field theory, a continuous theory, because in the end one wants to go to large scales, length scales. So one can as well start with a mesoscopic theory because it's much more convenient from the analytical point of view. So that's what one does. And so one starts with this. This is the Landau-Gisborne model, which we know the statics of this model will give you the classical ferromagnet. Well, this actually will be a vector field. And one can, then we just write Langevin equation for this field. So these were done in the 70s, mainly by Hohenberg, Halpering, and Ma. This is one paper, but maybe these two guys studied the dynamics of this family of models. And the situation here is simple in the sense that if you go to the critical manifold, you tune it to criticality. Basically, you tune R to go to the critical manifold. What one finds is that there is one relevant fixed point here, which is the celebrated Wilson-Fisher fixed point, which I think it's turning 50 this year or last year. And so this is for 3 dimensions, of course. For 3 dimensions, this is the relevant fixed point. And so these guys worked out the dynamics of this, and they computed the dynamical exponent for the physics near this fixed point. And they found something of around 2, a little bit above 2, 2.2 something, which is the value defined for the Ising model. It's at Ising. It's funny because in Spanish it's natural to say Ising, and we train ourselves to say Isings for the talks, just to, but Ising, it's easy. But which is, so this just alignment just gives you 2, which is quite far away. I mean, it's not that far away, but in the sense of a critical exponent, it's quite a distance, right? So it's not, clearly this is not enough to explain what's going on. So let's add the obvious thing, the next obvious thing, which is activity. So if we add activity, then we go basically to a Wigzig model, which is an active ferromagnet. So we write an equation similar to this one, basically. But now we'll say this: the interaction matrix or the adjacency matrix. Well, this depends on the positions, and the positions are not fixed, but they will move because this sigma is not a magnet anymore, but it's the direction of some velocity. Again, if you want to do renormalization group on this, you're better off going to a field theory. And that's basically what Toner and Tu did back in 1998. And so the field theory, which one can think of an active model A. So sorry, this model, this dynamics is known as model A in the Halpern-Hohenberg review. So that's the nomenclature we use. So basically, you can think this is to get an active model from here. What basically what you do is you replace the time derivative of the Langevin equation by the material derivative. That's the derivative you have in the Navier-Stokes equation. And you add the pressure, and you have to add some continuity equations because now the velocity field, it has to be linked to something. So there's something carrying the velocities. The velocities are linked to particles, so we have density of particles. So now we have two coupled fields. So this is the equation written in full, and you can think of this as the Halpring. So this would be model A plus activity, which are the red terms, or you can think of this as a fluid plus alignment, steered fluid plus alignment. Okay, so both these problems have been fixed. Now here we will impose the incompressibility conditions, which is good from the analytical point of view because it gets rid of one field, which is the density, but also what this does is that this turns the transition into continuous transition, and you can study it. You can study the critical point of this transition without. So it's no longer a first order transition, okay? So we just note in passing that you have some strange well, some quantities here that would be 1 for the Navier-Stokes equation, but here they're not necessarily 1 because of because the Galilean invariance can be broken. So you have to. Hope I didn't say something very wrong. Okay, so basically, so this model was studied by Tonner again, Tonner with Chen and Lee a few years ago, and what they find is that if you add activity, then the universality class changes. And so if you look at the critical manifold now you have 2 variables. So you have alignment here, and you have activity. So if the system, if you have no alignment, you have a fluid, and so you can see that you have some fixed point here with activity, which gives you an exponent of 1.5. If you have no activity, then you have the model A. So with alignment, we will go to this fixed point here, which gives you zeta equals 2. But if you have both things, you go to a new fixed point here, which has zeta equal 1.7, which is closer to what we want. So, but not quite there. But this is good in the sense that the activity is helping information propagate more quickly, and intuitively, that's why you get a lower critical exponent. You get better propagation of information. So that leads us to the third point. So what can you do to get the right exponent? And some here is the clue, because this is telling you that you want dispersion relation with the real part. So this is purely dissipative. This has a real part. It's not purely dissipative. You have inertial effects. If you have inertial effects, you expect to have some wave-like propagation, and waves will enhance propagation of information. So you can expect that the critical exponent will go down. Actually, this, not in the context of activity, but overdamped versus underdamped models was discussed quite widely in the 1970s. This is a very famous review by Halperin and Hohenberg, 1977, where they compare model A, which I always show you, with new models which have inertial behavior. And so the idea here is that we will start with model A, so we will add inertia to our activity. But so how is inertia added in the model A case? So let's do it in 2 steps. So if you have model A, to have an inertial model, you have to consider 2 fields. So you introduce another field, which is the spin, which is generating the rotations of the order parameter field. So these are the Poisson brackets that say this, that are saying that the spin is generating rotations. And then you write the equation. So these blue terms are what comes from simply using the Poisson brackets with the usual Landau-Gisborne Hamiltonian. And then you have these two other terms, which are the dissipative terms, that are the terms that will couple to the bath, to the bath, and give you allow you to thermalize. So to add activity, so sorry, and if you do this, well, this was done in the 70s, and the critical exponent goes from 2 to 1.5. So it lowers the exponent. So the bet here was, what if, sorry, where okay, here. What if we add inertia to the active model, overdamped model we have? Okay, so or you can conversely you can say, let's pick model G, which is model A with inertia, and then add activity to it. So it's basically the same time. So you start with model G with inertia, do this transformation, promote this to material derivatives, and add the pressure, add the incompressibility condition. And basically, that will be your theory. There's only just another thing I have to mention, which is that this coefficient here is in the original theories in the model G is just a Laplacian, because originally the spin field was a conserved field, which has to be conserved locally. Okay, so for us this need not be so. So we start with a Laplacian, but add a little bit of dissipation. By the way, you need this. If you don't put this, renormalization group will generate this term. So that's why we put it in the end. And so, well, I'm still have a few minutes, but I'm almost at the end. So after a quite long calculation, the picture, the final picture is basically this. So this is the critical manifold, or just at least a part of the critical manifold. And then we have this axis. So you have activity here, you have inertia here, and this is so this is the new inertia axis, and this is the axis which is the dissipation, the eta I introduced. And so the thing is, what we find is that if we start here with an active model without any dissipation, then this was the old fixed point where you have no activity. If you add activity, you go to a new fixed point, which is not the Toner fixed point, but it's a new fixed point with inertia in the conservative plane, which leads to a critical exponent which is around 1.35. This is a one loop calculation, so it's not exact, of course. And the other critical fixed point, the fixed point found by Toner, without inertia, here you can find if you add some dissipation, the system, the renormalization group flow goes towards the overdamped case. So this other plane, which is the overdamped plane, has this fixed point, which is the fixed point I showed you before for the fixed case, let's say. Okay. So what we argue is that this is the fixed point that's relevant for midges, for swarms, because although you expect to have some dissipation, if the system is finite, when you do RG, the flow stays near this fixed point for a very long time. And so if the system is finite, you will have to stop the flow before the flow flows away from this fixed point. And so this fixed point will rule the dynamics of a finite inertial system representing swarms. Okay, so to summarize, we started with zeta equals 2 from alignment, activity lowers it to 1.73, inertia lowers it to 1.35 about. So that's very, very close to the experimental results. Maybe too close for one loop calculation, but okay. That's it. Well, perhaps I'm over time, probably, but we have checked this with numerical simulations. You can check that this system, this is a microscopic version of our model with inertia, and this works. You can show that this works in the same way. Okay, so I'll be finishing here. These are my conclusions. Let me just have you the final slide with the names of my collaborators. So Andrea Cavagna, this is the group leader, and Irene Giardina in Rome. Stefania Melillo, Leonardo Parisi, mainly in charge of the experimental part, and PhD students that did calculations and simulations. And this is the last paper that more or less summarizes what I said today and the other work. So thank you very much.
Hi, Thomas. Very beautiful. Well, can you compare with systems that has no inertia, for example, and come back to the other exponent? Let's say, experimentally speaking, I know that it's very hard that you have computed in these swarms, but is it possible to have an idea if the theory works for other kinds of
I don't know when experiments. The theory works for the VICSEC model. You can do that. We also had these simulations. I did not show. I'm not aware of the experimental case without inertia. I mean, the systems we looked at, which are, well, these midges and starlings, and they're the inertial effects are important. That's actually, we started with inertia, thinking of inertia with Starlings, and then it turns out that it was good for midges too. But I don't know. Perhaps in a system with more dissipation, and a larger system, it has more dissipation, then it will probably go to the under overdamped limit. But I'm not aware of experimental results right now.
So that's very nice. Oh, sorry. Yeah, okay. Very nice calculation. So quick question. Since midges have a head and a tail, if you add polarity, so sort of polar active plus inertia, would you see would Z change a little bit, or maybe
Well,
that's just a silly question?
No, but the model is polar, actually.
It does have a polarization vector.
Yeah, because it's a Wigzig model. So
okay,
what happens
great.
is that it's at the critical point, so you don't have an overall order parameter, an overall velocity. But individually, the particles have polarity, yes.
Okay, great. So thank you for clarifying that. Thank you.
Okay, so let's think again.
Okay, thank you.